Welcome back to Topic 1 for AP Calculus, Limit of a Function. In this video, we're going to identify what is the limit of a function and then use graphs in order to visually see them. So let's first define what is the limit as a function. We have the limit as x approaches a of f of x equals L. So that's how this is read. Now basically what this means is as f of x gets closer and closer to L, as our value of x gets closer and closer to a from either side, however, x does not equal a. It gets closer and closer to a, but x does not equal a. We can see that in this example. So in order to evaluate a limit, we're going to use this method first in order to kind of come to our conclusion. Here we have the limit as x approaches 1 of x squared minus 1 over x minus 1. Now if we just try plugging in 1 for x, this is the same thing as 1 squared minus 1 over 1 minus 1. But here we get 0 divided by 0. Now we don't want to divide by 0, that's indeterminate. So let's try plugging in values that get closer and closer and closer to 1. Let's try x equals 1/2. If we plug that in to our function, that gives us positive 1.5. If we try plugging in 0.9, so 9/10, let's do a different color. 0.9 squared minus 1 over 0.9 minus 1. That gets us closer and closer to 1.9. 99 hundredths. If we get 0.99 squared minus 1 over 0.99 minus 1. That gets us to 1.99. Try even further, 0.999 or 999 thousandths. If we square that, subtract 1, and then 0.999 minus 1, that gets us 1.999. So if we look at all of these values, they're getting closer and closer to a number. They're getting closer and closer to the number 2. So this is saying that as x approaches 1, x squared minus 1 over x minus 1 gives us 2. Now what we did in that first slide there is we approached 1 from the left-hand side. So if we think about a number line, and we have our number 1, we were approaching 1 from the left-hand side because we had 1/2, 0.9, 0.99, 0.999. So this is called the limit as x approaches 1 from the negative side, or from the left-hand side, of x squared minus 1 over x minus 1. We can also try this from the right-hand side. So as limit as x approaches 1 from the positive side of x squared minus 1 over x minus 1. So let's try that and see what we get. If we plug in 1.5 here, we have 1.5 squared minus 1 over 1.5 minus 1. This gives us 2.5. If we plug in 1.1, we get 1.1 squared minus 1 over 1.5 minus 1. And that gives us 2.1. If we plug in 1.01, square it, subtract 1 over 1.01 minus 1, that gives us 2.01. So just like before, if we, if we look at these values, they're getting closer and closer and closer to the number 2. So these from the right-hand side also approaches 2. So we went in from the left-hand side before with 1 negative, and now we just came in from the right-hand side 1 positive. So we can actually see this on our graph, and this is approaching a value of 2 from our point right there. So because we came in from the left side and the right side, we can accurately conclude that the limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. So again, before we came in from the left-hand side, we did as x approaches 1 negative. Then we came in from the right-hand side as x approaches 1 positive. So then, because it came in from the left side and the right side, we can conclude that x approaches 1. Of this function, x squared minus 1 over x minus 1 gives us 2. Let's try another example. Here we're dealing with some trig. So we have to find the limit as x approaches 0 of cosine of pi over x. So let's try from the negative side. As x approaches 0 from the left-hand side, cosine of pi over x, we have a graph on the right-hand side that we can use for reference. So on the left-hand side, see how it's kind of oscillating? It's going back and forth and back and forth and back and forth and back and forth. It's not really settling down on a number. If we come in on the right-hand side, so 0 positive, it's also going back and forth and back and forth and back and forth and back and forth. It's also not settling down. So it does not settle down on a specific number. Instead here, it's oscillating. It's bouncing back and forth. So neither the left hand nor the right-handed limit will exist in this case. So we can say that the limit as x approaches 0 of cosine of pi over x does not exist. And DNE is like our shorthand for does not exist. Okay, now let's try with a graph. So here we have a function f is shown on the graph. The domain is all real numbers except x equals -4 and x equals 0. We're asked to use the graph to evaluate the following. So we're asked to evaluate a limit as x approaches 4 of f of x. So we want to look at our graph at 4. Here is 4. If we go up on our graph, we have a point right here at 5. So the limit as x approaches 4 of f of x is 5. The limit as x approaches 0 of f of x, if we go on our graph here, as 0, we look up, we have a point at 2. Now this is an open circle. We will talk about that later in later topics. But this is actually defined as a hole. Then we have the limit as x approaches -2 of f of x. So we want to find -2 on our graph here. But notice here, if we find -2, it gives us 3. And that's because it's connected on our graph right here. So we can come in from the left-hand side, we can also come in from the right-hand side. So this gives us +3. But I wanted to make a specific note that f of -2 equals 1. So if we're not applying a limit, but just if we have f of negative 2, our graph is shifted a little bit here, I apologize. But that gives us 1. But the limit as x approaches negative 2, so if we're kind of looking on our graph and looking where those curves lie, of f of x gives us that positive 3. So we have two different things. Because we have two different things here, this is called a discontinuity. We will talk more about that in future topics. If we have the limit as x approaches 3 of f of x, this gives us, hold on, let me get my eraser so I make it a little less confusing. As x approaches 3, again, we want to look on our graph here, but notice we have a jump actually. So from the left-hand side, it's approaching 1. From the right-hand side, we're approaching 4. So see how these values do not match. Here we also have a discontinuity, and there's a jump right here. So this limit does not exist, because if we look from the left-hand side, it's one value, but from the right-hand side, it's another. So since they don't match, we have that like gap literally in between, does not exist. Now the limit as x approaches 3 from the negative side, as we just did, gives us positive 1. And from the positive side, gives us 4. Let's look at another example here. Limit as x approaches negative 4 of f of x. So if we look on our graph, negative 4, here it's going in two different directions. So one way we're going down, but another way we're going up. So on the left-hand side of the limit, we go down to negative infinity. On the right-hand side, we go up to positive infinity. But we actually do not settle on a specific value from the left-hand side and the right-hand side. They do not match. So the limit as x approaches negative 4 of f of x does not exist. But as we just said, if we come in from the negative side, we go down to negative infinity. And from the right-hand side, we go up and up and up to positive infinity. Now if we look on our graph, as x approaches positive infinity, so we keep looking further and further and further to the right, it is approaching to this value at y equals 6. So at this value 6 right here. This is actually, as we will get to in topic 3, I believe, with, this is actually a horizontal asymptote. If we look on the the left-hand side, as x approaches negative infinity, it keeps going up and up and up to positive infinity. So it's not actually settling at a point. It's not getting infinitely closer to a point. It's just kind of keep going up. So it's going to positive infinity here. And that was topic 1 for EP Calculus on the limit of a function using graphs. Thank you for watching.